So here we have a steel ball of mass 0.75 kilogram. And as it is initially at rest, it is then dropped from a height of 30 meters above the ground. And then here's A, B, C, D, and E. If you need to, pause it, and then I'll show you how to attack it. All right, let's crack out part A. Part A wants us to find the initial mechanical energy. Mechanical energy, by definition, is potential plus KE initially. So if you look at this particular diagram, it says here the object is being dropped from rest. So I'm just going to go ahead and cancel out KEI. So therefore, I can just say that the initial mechanical energy is simply contributed by the gravitational potential energy, which is just PEI. So we know the function for PEI. PEI is just mghi. And here, m is given as 0.75, g is 9.8, and then hi here is 30 meters. Everything is in proper SI units already, so I'm just going to go ahead and crank out calculator work. So m being 0.75, g 9.8, hi being 30 meters above the ground. So if you do that on your calculator, you get a value of 220.5 joules. Okay, and that is part A. Let's crack out part B. Part B wants us to find the kinetic energy just before it strikes the ground. So I'll do this properly and then hopefully encourage you to use common sense. All right, the proper way to do this, to written out is the mechanical energy initially must equal to the mechanical energy at the very final frame. This is a conservative system. It didn't mention anything about air drag or anything like that. All right. Here, we just break up MEI into PEI plus KEI. Likewise, on the right side, we break MEF into PEF plus KEF. But as you can see here, I can cross out certain things. KEIs I can cross out because this initially starts at rest. And then PEF I can cross out because it says just before it hits the ground, implying that H is very, very, very small, which is essentially 0. So mgh would just be 0. So here we have a statement. It says the initial potential energy is equal to the kinetic energy at the very bottom, which makes sense, right? All of this energy that's stored due to gravity is going to convert itself to kinetic, all of it. So we should get the same answer. All right, the initial potential energy due to gravity, we already found this in part A. Part A, if you look at it on the right side, it says PI is equal to mghi, which is equal to 220.5. Well, if PI is 220.5, I can just substitute that in. PI here is 220.5, and that is your KEF, which makes sense. Potential energy got converted to kinetic energy, all of it. Okay, there we go. So the answer is the same as part A. And let's go ahead and crack out part C. Part C wants us to find the ball's kinetic energy after it has fallen at a distance of 5 meters. So I remind you that this the steel ball here is 30 meters above the ground to start, and it's only fallen 5 meters. So keep that in mind as we practice. Here, to find KE after it has fallen 5 meters, I'm just going to use conservation energy. Likewise, I'm just going to set this stuff up. I want to cross out KEI again, except I am not crossing out PEF here, right? It didn't say it fell the whole 30 meters. It said it's only fallen 5 meters, which implied that it's still in the air, which implied that it's still above ground. So don't be canceling stuff out unless it's appropriate. All right, so on the left side, we reduce this to just PEI. On the right side, we have PEF plus KEF. So let's go ahead and crack it out. It says KE. So you notice here for part C, I'm keeping KE as is. I'm not going to break it up into 1/2 mv squared. Okay. So as you practice, focus on what is being asked of you. And so don't break KE into 1/2 mv squared out of habits. So to solve for KEF, which is what I'm being asked to do, I'm just going to go ahead and subtract both sides by PEF. So I'm going to move PEF to the left side. So it's going to go from positive to negative. And then I'm just going to expand these two functions. PEI is mghi minus mghf, and that equals to KEF. But as you can see here, if you want to, okay, you don't have to do this step. At this point, you can just plug and chug. But I like to encourage you, as you see functions, learn to factor it out just in case you're asked to, select statements that are true. Here, both these terms have an mg, so you can factor it out. So factoring it out would imply that you just pull outside of the parentheses. So here we have mg outside and then hi minus hf. Well, we know everything already. So on the diagram here, right, it's 30 meters above the ground. It's fallen 5 meters, which I've drawn here for you. But that's not the distance you want to use, right? H is measured from ground up. So you actually want to do a little extra thinking here. Well, you've fallen 5 meters, which imply that you're still 25 meters above ground because the total height is 30 meters. So HF is 25 meters. So it's important that you don't just use values given in the statement. You actually have to know what you need. So in this case, I need HF. HF is measured from ground up. Ground up in this case being 25 meters. My HI is 30. So as you can see here, it's plug and chug time. 0.75 times 9.8 times 5 will give you about 36.75 joules. So KE it's about 36.75 joules after 5 meters of fall. Okay. All right, let's go ahead and crack out. Oh, you know what? Hold on. For part C, if you wanted to, you can actually do this. You can do KE, it's 1/2 mv squared. I know mass already. Mass is 0.75. Here's VF squared. I don't know what VF squared is, but what you can do is use your kinematic stuff, okay? If you want, you can use your kinematics. VF squared minus VI squared equals 2G delta Y. And I can apply this because this is a conservative system, meaning there's no energy loss due to drag or, whatever it is that it could possibly state. Here, VI, I'm going to cross out because that's 0. And then I know what 2 is. I know what G is. G is negative 9.8 because it's free falling. And I know that the object has fallen a distance of 5 meters, but really here delta y is your displacement. So displacement is a vector, so you need to put a negative sign because it's fallen down. Okay. Other than that, if you actually multiply these values together, you'll get 98 because 2 times 5 is 10. 10 times 9.8 is 98. But you notice here, I want to keep this as VF squared. I'm not going to square root it. Okay. Why? Because in KE, you need VF squared. So pay attention to what you're doing. I like to just keep it as VF squared here because I need VF squared. If you want, you can square root it, but then you plug it back in and then you're going to square it again. So I would say you're just like doing something and undoing it. So I'm going to keep this as VF squared. So VF squared is 98. So all I'm doing is I'm carrying down this function again. So KE is 1/2 mv squared, v squared being 98. And so I'm just going to plug that in the calculator and I'll get the same answer, okay? So pick a method that you like. Conservation energy is pretty safe. Kinematics, if you're pretty solid about it, feel free to use it. All right, other than that, you can see the answer is the same, 36.75 joules. Let's go ahead and crack out part D. Part D asks us to find the potential energy at 1.25 seconds. To find PE at 1.25 seconds, I need mgHF. Well, here mass is given as 0.75. G I know is 9.8. I don't know what HF is. Okay. However, what I can do is just use kinematics. Well, it says what is the potential energy at 1.25 seconds? Well, 1.25 seconds imply that it has fallen 1.25 seconds, so it's still above the ground. So here I can just use my displacement function. I'm going to cross VIT out because it's being released from rest. So here I just have displacement. It's 1/2 GT squared. Well, T is given. G we know. Okay, so I can just plug and chuck. G is negative 9.8. T is 1.25 because it said so in the problem. And here I'm just going to square that. If you square all this in a calculator, you'll get a negative 7.66, which makes sense to me. After 1.25 seconds, the object, the steel ball in this case, has fallen down 7.66 meters. But once again, keep in mind of what you need, right? You just found the distance that it fell, not the distance above ground. So watch my cursor, or watch my diagram. I just found that to be 7.66, and it's pointing down because it's fallen down 7.66. But the total height is 30. So what you just have to do a little thinking. Make sure you use the right height. So all you have to do is take 30 minus the distance it has fallen at 1.25 seconds, and then that gives you the distance that's above ground, which in this case is 22.34, and that is what I'm going to plug in. So as you can see in my work, to find PE, I need mgh. I know m, I know g, I didn't know h. Now I just figure out what h is, h being 22.34 meters because it has to be measured from above ground. And if you plug that in your calculator, you get 164.2 joules, okay? All right, and that's the answer for part D. Now, if you want to, you can also use conservation mechanical energy, like I have here. MEI equals MEF, and then you can just start crossing things out. KEI is 0, and then PEI equals PEF plus KEF. PEF exists in this case because it's only fallen 7.66 meters, which implies that it's still above ground. All right, so if you actually solve for PEF, move KEF to the left side, which makes it minus. So here we can just expand it. PEI we already know from part A and B, right? The initial potential energy is 220.5 joules. Well, I know I can break up KEF into 1/2 mvf squared. That will give me PEF. But I highlighted VF squared here because, well, I don't know what VF is, okay? But I can find VF real quick just using my kinematics. The function to find final velocity is acceleration times time plus VI. Here, acceleration being g because it's in free fall. Well, I know VI is 0, so I'm just going to cross that out. So I can just plug in g being negative 9.8, t being 1.25 seconds, and I know my VF in this case is negative 12.25. So it's negative is on its way down, right? So the speed is 12.25, but the velocity is negative 12.25. Other than that, I just found VF, so I'm just going to plug and chuck. All right, I'm just going to carry this function down. There's the 220.5 joules minus 1 half, 0.75 I carry down. And so instead of VF, I plug in negative 12.25 square. Now here, you don't really have to plug in this negative sign because you're going to square it anyways, right? Squaring a negative will give you a positive. And this is speed. So I just plugged it in here just for kicks and giggles. But if you're paying attention, the 1 half mv squared, all you have to do is use the speed. So leave out the direction. But if you have good habits and you use parentheses, a negative square will turn into a positive. All right, other than that, calculator work time. So if you simplify all this on your calculator, you get 220.5 minus 56.27, and then that will give you an answer of 164.2 joules, which again matches what I got using this other strategy, simply just looking at PE and finding the height above ground. Okay, pick whatever method you like. Hopefully it makes sense. All right, let's crack out part E. Part E asks you to find the instantaneous speed of the ball when it's 10 meters above the ground. All right, so I'm going to set up conservation energy again. I'm going to cross out KEI again. But here, keep in mind that you're trying to find the speed at 10 meters above the ground. Well, speed is hidden in KE. So here, when you get to here, you have to know what to look for or solve for, right? Or isolate for. Here, I'm going to isolate for KE. Why? Because KE has the velocity function or the speed function. All right, so I'm just going to move PF to the left side. So therefore, it becomes minus. And I can just expand this stuff again like I've done before. And as you can see here, M cancels out in all the terms. Okay. So to get VF squared by itself, the next thing I'm going to do is I'm going to multiply both sides by 2. Okay. So, oh, by the way, here you can factor it out. I just factored it out. I like factoring stuff out. Just it looks a little cleaner, but it's up to you. I'm just going to multiply both sides by 2. So here I have 2G parentheses HI minus HF. And then we know everything already. 2, I got carried down. G 9.8. HI being 30. HF here being 10. Now, I can actually use this 10 in the problem because it says 10 meters above ground. And that is how H are being measured. H in potential energy is measured from ground up. So in this case, it says 10 meters above ground, which implies that it's 10. Okay, so you don't have to do any thinking for this one. Other than that, if you do 2 times 9.8 times 20, you'll get 392. And then the square root of 392 will give you about 19.8 meters per second. And it says speed, so I'm just going to leave it as 19.8 meters per second without any direction. And if you don't like that, you can, again, use another strategy, as I did before in part D. We know the final velocity function can be calculated using acceleration times time plus VI. Here, I'm going to cross VI out. I know G is negative 9.8, but what I don't know is how much time it took to fall 20 meters, okay? So keep in mind, it's 10 meters above ground, which implied that it has fallen 20 meters. Otherwise, you'll get played by just looking at numbers and not knowing what it represents. So here in my displacement function, I'm going to cross VIT out. So the only thing I'm left with is just 1/2 GT squared. Here, my displacement is negative 20. It's negative 20, not 10, okay? Because this is 10 above ground, which implies that you've fallen down 20 meters. So because you're falling down, that's a negative sign. Delta Y is 20 meters. And then it's 1/2 GT squared, but 1/2 times negative 9.8 is just negative 4.9. And then there's the t squared. I need to get t squared by itself, so dividing both sides by negative 4.9. And if you do 20 divided by negative 20 divided by negative 4.9, you get about 4.08. But that's t squared. And then you got to square root it to get t by itself. So the square root of 4.08 is about 2, or 2.02 in this case I give you. And then once you know t, it's super easy. Plug it back in there, right? Final velocity is g times t. We just found t. So g being negative 9.8, t being 2.02. If you multiply that, you'll get negative 19.8. Now, I know this is negative because this function allows you to find velocity, right? Because velocity has a direction. However, the question asks you to find the instantaneous speed, which is really VF. But because of speed, you can just give the absolute value of this answer, which is just 19.8, which is the same magnitude over here. All right. Other than that, I hope that helps. Stay nerdy. Don't be whack.